If your mind will not power down, try one quiet thought. Reality might be branching in tiny unseen ways. Tonight, 120 calm facts will guide you, and one multiverse idea may be almost testable. If you want this ready at bedtime, tap, like, and save. If you are awake enough, leave one quiet word: multiverse. Before we go anywhere strange, let's make the phrase parallel universe feel simple and safe. In this video, it will mean a reality that is separate enough from ours that it does not directly affect us day to day. That separation can be physical, like distance and cosmic barriers, or it can be quantum, like histories that no longer overlap in any practical way. Either way, we are talking about ideas in physics, not a warning sign. A model is a story nature might be telling, written in careful language. And a hypothesis is an open door, not a demand that you believe. So if your mind starts to spin, return to one calm anchor. Parallel universes are separate descriptions of reality, used to explain what we observe. Now, there are two big families of ideas that people often mean by parallel universes. The first family is quantum branching, sometimes linked to the many worlds interpretation. This is the idea that tiny quantum events can lead to different outcomes, each outcome continuing as its own branch. The second family is cosmological multiverses, which come from thinking about the early universe and vast space. These include bubble universe ideas in cosmic inflation, and also the possibility of an infinite universe. Those two families feel different, and that is useful. Quantum branching is about the rules of measurement, like what it means to get a single result. Cosmic multiverses are about geography, like what might exist beyond what we can see. If you like a micro choice to settle your mind, you can pick one to hold lightly, which feels calmer right now. Quantum branching, or cosmic bubbles. You do not need to answer out loud. Just notice which mental image is gentler for you. Now let's place these ideas on a small map of physics so nothing feels tangled. In quantum mechanics, we use a mathematical description that can include many possibilities at once. When we measure, we get one definite outcome. Different interpretations are different stories about how that definite outcome appears. Some stories add a collapse, where the wave-like description snaps into one result. Some stories keep the wave-like description and say reality effectively splits into branches. And some stories add hidden details, so the result was always decided in a deeper layer. In this first part, we will not argue for one story. We will just name the stories and keep them tidy. Next, there is cosmology, the study of the universe as a whole. Cosmology asks how the universe began, how it expanded, and what might exist beyond our observable horizon. Inflation is a popular idea in cosmology that says the early universe expanded extremely fast for a short time. In some versions of inflation, that process can create separate regions, like bubbles, that grow into their own big universes. Those bubbles would be far beyond our reach, separated by expanding space. That is one common meaning of a multiverse in cosmology. And then there is the simpler thought. If space is infinite, then it contains an enormous amount of room for repetition. In an infinite universe with only so many ways to arrange matter in a region like ours, patterns could repeat very far away. Not close, not reachable, but conceptually there. That idea is often called a distant copy picture. It is not magic, just the logic of vastness. Another corner of our map is string theory, which is a framework that tries to describe particles and forces in a unified way. String theory often suggests extra dimensions, curled up too small to notice directly. It also suggests that physics might allow many stable patterns, like many possible settings for the laws of nature. Physicists sometimes call these patterns different vacuum states, like different valleys in a landscape. If different regions of space settle into different valleys, they could have different kinds of physics. That connects string theory to multiverse discussions, but it is still careful, conditional work. For bedtime purposes, you can hold a gentle summary. Quantum ideas focus on outcomes. Cosmic ideas focus on regions. String theory ideas focus on possible rule sets. Now, a comforting boundary. None of these ideas require you to imagine chaos breaking into your life. Even if there were other branches or other bubbles, they are, by definition, separate enough not to bother you. They are used to explain observations, not to predict sudden visitors. And because they are scientific ideas, they come with limits and open questions. Some parts might be testable, some might not, and we will be honest about which is which. That honesty is part of the calmness here. Now, a quick guide for listening, since this is designed for repeat play. You do not need to remember every detail. Let the details pass by like slow clouds. Try to keep only the main picture of each section, like a single postcard in the mind. When you hear a new term, you can treat it like a label on a drawer. We will come back and open the drawer slowly, one at a time. Later, near the end, I will gently recap key ideas in a looping pattern, so your mind can drift without losing the thread. And when we reach the numbered facts, you will have simple re-entry points. If you wake up during the night, you can rejoin at any fact number. No need to rewind, no pressure to catch everything. This is calm learning built to be predictable. So for now, just remember this soft definition. Parallel universes are ways reality might be arranged in separate tracks that do not directly touch. With that map in place, we can step into the quantum basics, slowly and clearly. Let's take quantum mechanics and make it feel like a quiet room, not a hard test. You do not need equations tonight. You only need a few gentle pictures that behave well in the mind. The first picture is superposition. Superposition means a system can be described as having several possible outcomes at once before you check. Not as a messy pile of stuff, but as one clean rule set that includes multiple possibilities. Think of it like a musical chord, not a shouting crowd. One description, several notes, and the world decides what you hear when you listen. In quantum theory, the notes are called amplitudes. An amplitude is not a chance by itself, but it shapes the chance you get in the end. Two amplitudes can combine in ways that look like overlapping ripples on calm water. Sometimes they add together, making an outcome more likely. Sometimes they cancel, making an outcome less likely. This is why quantum theory can predict patterns even when single outcomes seem random. If you repeat a quantum experiment many times, you do not get pure chaos. You get a stable pattern, like a gentle texture appearing in the long run. That pattern is one of the most practical reasons physicists trust the theory. Now, a word you may hear often is wave function. For bedtime listening, you can treat the wave function as a description. It is a bookkeeping tool that tells you how to assign probabilities to outcomes. Some interpretations treat it as something real in the world. Other interpretations treat it as information about the world. You do not have to pick a side right now. Either way, it is not a tiny physical fog you need to imagine filling your bedroom. If that image feels weird, let it go. Keep the calmer idea. It is a compact description of what outcomes you might see. Superposition shows up in experiments in a quiet, measurable way. One classic example is interference, where probabilities form stripes or bands rather than smooth fades. Those stripes are the fingerprint of amplitudes adding and canceling. You can picture them as soft waves meeting and shaping a pattern. No drama, just structure. Now we move to the second picture, entanglement. Entanglement can sound mysterious, but we can say it plainly. Entanglement means two or more systems can share one combined description, and that combined description can tie their measurement outcomes together. So when you measure one, it changes what you should expect from the other, not because a signal shoots between them, but because the relationship was already written into the shared description. A calming anchor is this: entanglement is about correlations. It is about how answers line up when you compare them later. It is not about sending messages faster than light. Physics keeps its speed limit intact. You can have strong correlations without any usable instant communication. Imagine two sealed envelopes prepared together. Opening one does not send information into the other envelope. It just reveals what the pair was like as a pair. That envelope image is not perfect for quantum theory, but it captures the calm logic. The surprise is in how deep the correlations can be. Experiments have shown that nature allows correlations that are stronger than what many older classical intuitions would expect. Yet those correlations still do not let you control outcomes to transmit a message instantly. So you can keep the gentle summary. Entanglement links results, not with a shout, but with a quiet consistency. This matters for many worlds discussions because it helps explain coordination. If outcomes branch, entanglement helps keep related outcomes aligned across the branches in a lawful way. It helps make sure the world you experience has consistent stories inside it. When you measure one part of an entangled pair, your experience of the other part will fit with it. Not by magic, but by the structure of the shared description. Now, we arrive at the measurement question, the one sentence that stays open. When does a possibility become a single experience? That is the central puzzle of interpretation. The mathematics of quantum theory can tell you the probabilities for outcomes, but the mathematics by itself does not always tell you what becoming real means. Different interpretations tell different stories here while keeping the same successful predictions. Some say the wave function collapses, selecting one outcome. Some say all outcomes continue, each in its own branch. Some say hidden details pick the outcome, even if we cannot see those details directly. And some say the act of measurement is best understood as updating knowledge, not changing reality. You can treat these as different narrations laid over the same score. Same music, different commentary. Here is a soft check-in, just for your attention. If you had to choose which feels calmer, one reality with one outcome or many quiet realities that never meet, no need to answer out loud. Just notice what your mind prefers tonight. Now we place one small open loop, so your brain has a gentle thread to follow. In a few minutes, we will talk about decoherence. Decoherence is a process that helps explain why the everyday world looks solid and classical. It explains why those quantum possibilities stop interfering in practice. It does not necessarily tell you which interpretation is true, but it tells you why superposition becomes hard to notice for big, messy objects like tables, air, and bodies. It is like the difference between a clear mirror and a fogged mirror. The information gets spread into the environment, and clean interference becomes nearly impossible to restore. That is the calm bridge between the quantum world and your familiar world. Before we go there, let's make the basics feel settled. Superposition is one description that includes multiple possible outcomes. Amplitudes can overlap, adding or canceling like gentle ripples. This creates predictable patterns across many trials, even when single outcomes vary. Entanglement is a shared description that links results across systems. It creates strong correlations without sending faster than light signals. And the measurement question is the interpretive fork in the road. Same predictions, different stories about what is really happening. With these basics in place, we can meet the interpretation that turns possibilities into parallel branches. We will do it slowly, with calm language, and with clear boundaries between experiment and story. Now we meet one of the calmest and strangest stories people tell about quantum theory. It is often called the many worlds interpretation, linked to Hugh Everett in the 1950s. To keep things gentle, we will frame it as a choice about rules, not a cartoon of endless portals. Many worlds begins with a simple preference: use as few extra assumptions as possible. In standard quantum mechanics, the Schrödinger equation smoothly evolves the wave function over time. That smooth evolution works extremely well in experiment. But there is a puzzle about measurement. When we measure, we seem to get one definite outcome, not a blend of outcomes. Some interpretations add a special rule called collapse. Collapse is the idea that at measurement, the wave function suddenly jumps to one result. Many worlds asks a quiet question. What if we do not add that extra rule? What if the Schrödinger equation is always true, even during measurement? In that picture, the wave function never needs to snap. It simply keeps evolving, smoothly, all the time. People sometimes describe this as no extra rules. It is not that many worlds piles new universes on top of the old ones. It is that it refuses to add a special exception. That is why some physicists find it conceptually neat. It feels like a single law applied consistently. At the same time, it can feel emotionally odd. Because if the wave function keeps everything, then all the outcomes remain in the description. And the world you experience is only one part of that description. Here is a soft mental poll, just for your attention. Does no collapse feel elegant to you or unsettling? You do not need to decide. Just notice your reaction and let it pass. Now, a calm historical note. Everett proposed his approach in the 1950s when the meaning of measurement was still a lively debate. He suggested a relative state idea. Instead of one absolute outcome, outcomes are relative to the observer's state. Later, the label many worlds became a popular shorthand. The label can be misleading because it sounds like separate universes are being added. But in the technical heart of the idea, it is about the one wave function evolving without exceptions. So what is branching in this context? Branching is not usually imagined as a loud cosmic split. It is more like two paths in the same landscape that quietly stop crossing. In many worlds, measurement is a physical interaction. The system interacts with the measuring device and with the environment around it. That interaction creates a combined state where different outcomes are correlated with different records. One outcome is correlated with one pointer position. Another outcome is correlated with another pointer position. And crucially, those records become hard to mix back together. So you can think of branching as a separation of histories. A history is a consistent chain of records. Once those records are laid down in many places, the histories stop overlapping in any practical sense. In the usual many worlds story, branches do not chat. They do not send messages across the split. They do not collide, merge, or swap people. They simply become mutually unaware because interference between them is effectively gone. This is why branching can be described as parts of the wave function stop interfering. It is a quiet loss of overlap, not a dramatic tear. If you like a gentle metaphor, imagine two gentle ink drops in water. At first, they are concentrated and could be recombined in principle. As they spread and mix with the whole glass, separating them becomes effectively impossible. Branching feels a bit like that spreading. It is not that the information is destroyed. It is that it becomes distributed into too many details to bring back together. Now let's anchor this with an example that feels familiar. A coin flip is a good symbol of chance, but an ordinary coin flip is mostly classical physics. So instead, imagine a coin flip that is powered by a truly quantum event. For example, a device that triggers based on a single photon passing or not passing a filter. You connect that trigger to a little mechanism that drops a coin onto heads or tails. Before you check, the quantum description includes both possibilities. Photon passed. Coin becomes heads. Photon did not pass, coin becomes tails. In many worlds, when the interaction happens, the combined state includes both outcomes, each tied to its own record. There is a record in the device, a record in the air, in scattered light, in tiny vibrations, and in a moment, a record in you when you look. From your point of view, you experience one result. You see heads, or you see tails. You do not feel split. You do not watch two outcomes at once. You simply find yourself in the branch where a particular record is consistent. Meanwhile, The theory keeps the full structure of outcomes in the wave function. So in this story, your experience is not an exception to the law. Your experience is one thread inside the law. That is the promise many worlds tries to keep. One equation always. Now you might wonder, if all outcomes exist, why does it still feel like chance? Why do you feel uncertainty before you look? And why do the frequencies of outcomes match the usual probability rule in experiments? This is the famous probability question in many worlds. We will not do the full debate right now. We will treat it as a slow teaser and return later in the philosophy section when the pace is even softer. But we can name the main styles of answer, just so your mind has a drawer for them. One style of answer uses something like decision theory. It tries to show how a rational agent should bet, knowing they will branch. Another style of answer talks about typicality. It says that most observer moments find frequencies that match the standard rule in a suitable sense. And the standard rule itself is often called the Born rule. The Born rule connects the size of an amplitude to the probability of an outcome. Many world supporters work to explain why that rule emerges from the branching picture, rather than being added as a separate postulate. Critics argue that the story still feels incomplete, or that probability is being smuggled in by assumptions. That debate is real, and we will handle it gently later. For now, the important bedtime idea is simpler. Many worlds keeps the same successful quantum mathematics. It offers a way to talk about measurement without a special collapse moment. It says outcomes become separate, consistent branches when interference between them effectively disappears. And it says you, as an observer, naturally experience one branch because your records are part of the branching structure. If you notice your mind getting too active, return to a calm sentence. In many worlds, measurement is just interaction, and interaction creates separate, non-overlapping records. Now we can set up the next step. To make branching feel less mysterious, we need the quiet process that separates branches in practice. That process is called decoherence. Decoherence will help explain why the everyday world looks classical, even if the underlying description remains quantum. And it will give us a clearer sense of why branches stop overlapping without any loud metaphysical jump. So take one slow breath, and we will move into decoherence, softly, one idea at a time. Along the way, we will also plant a small retention loop. Later, when we talk about quantum computers, we will return to the feeling of branchy computation as a metaphor, not because a computer literally visits other worlds, but because the mathematics of superposition can look like many paths being explored at once. For now, we simply keep the main picture. One equation smoothly evolving, many possible outcomes in the description, and a quiet branching into separate records as the world interacts. Now we add one quiet idea that makes many worlds feel less spooky and more mechanical. It is called decoherence. Decoherence is not a new law of physics. It is what the usual quantum rules predict when a system touches its surroundings. The core thought is simple. The environment keeps records, not written in ink, but stored in tiny correlations. Light bouncing off an object carries information about it. Air molecules bumping into it carry information about it. Even gentle warmth, as infrared light, carries information outward. When a system interacts with the environment, the system and environment become entangled. That entanglement spreads information into many degrees of freedom. Some of that information is called phase information. Phase is what allows quantum possibilities to interfere like clean ripples. When phase information becomes spread out into the environment, interference becomes extremely hard to recover. Not always impossible in principle, but practically out of reach for ordinary, messy conditions. So the main result of decoherence is this: different outcomes stop interfering with each other. They stop producing the crisp quantum ripple patterns that would reveal their overlap. And once interference is gone, each outcome can behave as if it is on its own classical track. This is one reason the world looks solid and definite most of the time. It is not because quantum theory turns off at large scales. It is because the environment is always listening, always recording, always mixing the details into the background. You can picture decoherence as a kind of information leak. The system's delicate relationships leak into the surrounding world. And the surrounding world is enormous compared to the system. It is like whispering into a crowded, quiet hall. Your whisper is still there, in principle, in the air's motion. But it is spread so widely that you cannot gather it back into a clean sentence. Decoherence is that spreading, but for quantum phase. Now, there is an important boundary that keeps this calm and honest. Decoherence does not pick one outcome. It does not make a single result happen by itself. Instead, it explains why multiple outcomes do not interfere with one another anymore. It explains why, after the environment has recorded the situation, the outcomes behave like separate, non-mixing branches. So, decoherence helps with the appearance of a classical world. It explains why you do not see a chair smeared across the room like a ghostly blend. It explains why you do not see interference patterns from everyday objects. And it does this without invoking a conscious observer as the cause. Your mind is not required for decoherence to happen. Any interaction that spreads information into the surroundings can do it. That is one reason decoherence became so central in modern discussions of quantum foundations. Now let's address the famous image people bring up: the cat in a box. The cat story is a thought experiment meant to highlight discomfort, not to describe real lab practice with pets. If you imagine a large object like a cat in a superposition, you are imagining something extremely vulnerable to decoherence. A cat is warm. A cat is surrounded by air. A cat emits and absorbs light. A cat has countless internal moving parts. All of those are channels for the environment to record information. So, under normal conditions, large objects decohere incredibly fast. So fast that any delicate interference between cat states would be lost essentially immediately. That does not mean the cat is magically forced into one outcome by decoherence. It means the different outcomes become unable to overlap and interfere. They become like separate stories that cannot be recombined by any practical means. This is why we do not see macroscopic superpositions in daily life. Not because they are forbidden by the math, but because the world is too interactive, too information-rich, too good at recording. In special laboratory conditions, physicists can reduce decoherence. They cool things down, isolate them, and shield them from stray interactions. That is how they observe quantum behavior in larger and larger systems. But outside those careful conditions, the environment is like a constant gentle wind, always smoothing details, always blending delicate phases into the background. Now, here is the calming image for decoherence. Imagine footprints in smooth sand at night. Interference is like crisp footprints that clearly show where the walker stepped. Decoherence is like a soft wind that quickly blurs the edges. After a while, the sand still holds some trace of the story, but not in a neat, readable pattern you can follow. The information is still present, scattered in many grains. Your experience is like the smooth path you can walk in the morning. One clear trail, one set of records that agrees with itself. Not every possible footprint that could have been. This footprint image also hints at why branches stop overlapping. Two sets of footprints could overlap and form a visible pattern if they stayed crisp. But once wind smooths them, the overlap becomes meaningless. In the quantum case, the wind is the environment recording and dispersing phase information, and the smoothing is the loss of interference between outcomes. Now, a small micro-engagement to keep your attention gentle. Which metaphor feels easiest for you right now? Ripples, footprints, or branching paths? You can just choose one and let the others float away, because we will reuse that chosen metaphor as a calm anchor later. Now, one more careful point. decoherence is widely accepted as a real physical process. It is not an interpretation by itself. Different interpretations can all use decoherence. Many worlds uses it to explain why branches behave independently. Collapse models may still use it as part of how measurements look. And other interpretations use it to explain why certain outcomes become stable records. So decoherence is like a bridge. It connects the quantum description to the classical appearance we live inside. But it does not, by itself, settle the deeper question of why you experience one result rather than another. That question is where interpretations differ. And that sets up our next open loop, softly. Next, we will compare a few of the main interpretational stories. Some add a real collapse. Some add hidden variables. Some keep only the smooth equation. We will do it briefly, calmly, and without debate mode energy. For now, let decoherence be your steady ground. The environment records information. That recording spreads phase. Interference fades. And the world looks classical, even if the underlying math remains quantum. Many worlds is one story about the same quantum mathematics. Now we'll visit a few other stories, softly and fairly. Think of these as different ways to narrate the same set of successful predictions. In most everyday experiments, the calculations come out the same. What changes is the picture you hold in your mind. And for sleep, the picture matters. We'll start with something often called the Copenhagen view in a broad sense. Copenhagen is less a single doctrine and more a family of attitudes. The common mood is practical. Use the theory to predict measurement results and do not demand a literal picture of what the wave function is. In some Copenhagen-style variants, collapse is treated as a real physical rule. The wave function evolves smoothly. Then at measurement, it jumps to one outcome. In other variants, collapse is treated more like an update of knowledge, like changing your expectations when you learn new information. In that knowledge-focused view, the wave function is not a physical cloud in space. It is a tool for assigning probabilities to what you might observe. So when you measure, you update the tool. The calm benefit of Copenhagen-style thinking is simplicity in the lab. Physicists can focus on what they can prepare, what they can measure, and what the statistics will be. It avoids big claims about hidden worlds or invisible structures. It also matches how many people learn quantum theory at first. Solve the problems, match the data, keep the metaphysics light. If you like a soothing mental anchor for Copenhagen, it is this. The theory is a user manual for outcomes. Now we move to a very different picture called Bohmian mechanics, sometimes nicknamed pilot wave theory. This story tries to keep two comforting ideas at once: definite particles and a guiding wave. In Bohmian mechanics, particles have precise positions at all times. They do not float as vague possibilities. At the same time, there is a wave function that evolves by the usual quantum rule. That wave function guides how the particles move. So instead of collapse, you have a single actual path traced by real positions. The wave still contains many possibilities, but the particles follow one trajectory. This can feel intuitively steady. There is always a concrete configuration, even when you have not looked. Now, Bohmian mechanics comes with an important feature. The guiding influence is non-local. That means the behavior of one particle can depend on the configuration of others, even when they are far apart. This non-locality does not allow you to send controllable messages faster than light, but it does mean the underlying description is more interconnected than classical physics usually feels. That interconnection is one way pilot wave theory reproduces the strong correlations we see in entanglement experiments. So in a calm phrase, Bohmian mechanics says, one world, definite positions, guided by a wave. It aims to explain quantum weirdness by adding hidden details rather than multiplying branches. Some people find that soothing. Others find the non-local guidance harder to accept. Either way, it is a coherent alternative picture that matches quantum statistics in many standard cases. Now we turn to a third family of ideas called objective collapse models. These are sometimes associated with names like Girardi, Rimini, and Weber, and also related proposals. We do not need the names tonight. We only need the style of idea. Objective collapse models add a small new ingredient to quantum theory. They propose that collapse is a real physical process, not just an update of knowledge. And they propose it can happen spontaneously, very rarely, even without a measurement device. In this story, the wave function usually evolves smoothly, as usual. But once in a while, a gentle random collapse happens. For tiny systems, such collapses are so rare that ordinary quantum behavior remains visible. For large systems made of many particles, the chance of collapse becomes effectively much higher. So, macroscopic superpositions would not last long. They would be quietly suppressed by the collapse process itself. The goal is clear and calming. Explain definite outcomes in one world without branching into many worlds, and do it without requiring a special role for observers or consciousness. It is nature that chooses through a built-in process. Now, these collapse models are not just philosophy. They are designed to be testable, at least in principle, because they predict small deviations from standard quantum theory in certain regimes. That is part of their appeal. If the world has an objective collapse mechanism, very delicate experiments with larger and larger quantum systems might notice something. This sets a gentle open loop for later. Much later, we will mention the kinds of experiments that try to probe macro-quantum behavior. Experiments with interference in large molecules, with ultra-cold mechanical resonators, and with carefully isolated systems. Not because we need technical detail tonight, but because it is calming to know some ideas come with real, measurable stakes. Now, a soft comparison that keeps everything tidy. Copenhagen-style views tend to say, focus on predictions and measurements, and be cautious about what the wave function means. Bohmian mechanics tends to say, there is one actual configuration, guided by a wave that carries the quantum structure. Objective collapse models tend to say, add a real collapse process so macroscopic definiteness is built in. And many worlds tends to say, keep the smooth equation always, and let branching handle the appearance of outcomes. These stories disagree about what is really happening, but they share the same practical success across a wide range of experiments. That is why physicists can argue calmly about interpretation while still building lasers and semiconductors. The devices work either way. Now, a small engagement moment just for your attention. Which explanation feels most soothing? Minimal talk beyond outcomes, hidden variables with a guiding wave, or gentle collapses that keep one world? You can just pick the one that feels calmest tonight. No need to commit. In this series, we will treat each interpretation as a lens. We will use the lens when it helps explain an idea, then set it down again, because the goal is not to win a debate. The goal is to give your mind a smooth track to follow. And now that we have a few lenses on the table, we can see why famous thought experiments were invented. They are little stories designed to stress test these pictures. So next, we will tell a few of those thought experiments softly, not as puzzles that demand an answer, but as calm scenes that show why these quantum stories exist at all. Now we'll visit a few famous thought experiments told in a soft voice. They are not meant to frighten you. They are meant to make one question easier to see. How do quantum possibilities become a single lived experience? If you like a calming phrase to hold, try this. Possibilities become experiences. First is the story often called Schrödinger's cat. Tonight, we treat the cat as a metaphor, not a literal scene. It is a way to scale a tiny quantum uncertainty up to human size. Imagine a sealed setup with a quantum trigger inside. The trigger has two possible outcomes, like yes or no. If the trigger does one thing, a larger effect follows. If the trigger does the other, that effect does not happen. In the quantum math, both outcomes can appear in one description before you look. That single description is what people call a superposition. The tension begins when we ask what that description means physically. Everyday life feels like one outcome at a time, but the math can represent multiple outcomes together. So the cat story asks, gently, where the one outcome feeling comes from. Different interpretations answer that differently. In some collapse-style views, one outcome becomes real at a particular moment. In many worlds, the full structure continues, and experience follows one branch. In pilot wave ideas, the configuration is always definite, even before you check. So the cat story is less about cats and more about definitions. Was the cat ever truly both in reality or only in the calculation? That is the interpretive fork. Now we add a calmer, modern ingredient: decoherence. Decoherence is what happens when a system interacts with its surroundings. Light, heat, air, and internal motion all count as surroundings. Those interactions spread information into the environment, and they spread it into so many tiny details that it cannot be gathered back. This is why cat states are so hard to maintain. A large, warm, complex system leaves traces everywhere, almost immediately. Those traces carry rich outcome information in practice. And once the information is out, clean interference between outcomes fades away. So decoherence explains why we do not see macroscopic superpositions in daily life. It explains why the world looks stable and classical most of the time. But keep one important boundary so we stay honest and calm. Decoherence does not select one outcome by itself. It explains why outcomes stop overlapping, not why one is singled out. That is why interpretations still differ after decoherence enters the picture. So the cat paradox becomes a gentle lesson. Quantum theory predicts the statistics beautifully, but it leaves room for different stories about what happens during measurement. Now, we move to the second thought experiment, called Wigner's Friend. This one can sound personal, but it is really about consistent descriptions. Imagine a small laboratory with an observer inside. That observer measures a quantum system and writes down a result. From inside, the situation feels ordinary. They saw a definite outcome and they made a record. Now imagine a second observer outside the lab. The outside observer has not opened the lab or read the record. From their perspective, the lab is part of the physical world, so they may describe the whole lab, including the record, using quantum rules. If they do, the lab can be described as a combination of possible recorded outcomes. So we have two viewpoints that sound different. Inside, one outcome experienced. Outside, multiple outcomes still in the description. The calm takeaway is not that minds create reality. The takeaway is that we must define measurement carefully. What counts as a measurement for the outside observer? When does a record become irreversible in practice? Decoherence helps here because records spread into the environment. Once information leaks outward, the outside observer cannot access clean interference anymore. So even if the outside description is written in quantum terms, it behaves like separate, stable alternatives. Different interpretations then say different things about what is really going on. Collapse views tend to say a real selection happens at some stage. Many worlds tends to say both alternatives persist in separate branches. Other approaches may say the wave function is a tool for predictions, not a literal picture. In every case, the puzzle pushes language to be precise. And precision, when slow and gentle, can feel soothing. If your mind wants to settle, return to the phrase again. Possibilities become experiences. Now we drift to the third family of curiosities, delayed choice and quantum eraser ideas. These can sound like time is being bent, but the calmer truth is about information and interference. In interference experiments, a pattern appears only if alternatives remain coherent. Coherent means the phase relationships are intact. If the world keeps track of which path was taken, coherence is lost. When coherence is lost, the interference pattern disappears. A delayed choice setup changes what kind of information becomes available. Sometimes that choice is made after the particle has entered the apparatus. To a classical mind, that can feel like the later choice reaches back in time. But quantum theory does not require a single classical story in the middle. It requires consistent probabilities for what you can actually observe at the end. The math stays orderly even when our intuition feels stretched. A quantum eraser variation highlights the same point. It arranges things so which path information can be available or effectively unavailable. When which path information is available, interference is washed out. When which path information is not accessible, interference can show up in the right comparisons. Often, that right comparison means sorting results by correlated records. So it can look mysterious until you remember the role of correlations. No signal is sent to the past. No later choice changes a recorded earlier fact. Instead, the full story is about what information exists and how results are grouped. If that feels like a lot, keep one soft sentence. Interference needs privacy. When the path is recorded, interference quietly fades. This sets up a gentle bridge to a later topic. People sometimes use branching metaphors when they talk about quantum computing, not because computers literally travel between worlds, but because superposition and interference can act like many roots contributing to one answer. Amplitudes can reinforce useful paths and cancel unhelpful ones. That is the same ripple logic used for computation. We will return to that later, slowly, with no technical weight. For now, these thought experiments serve one calm purpose. They show why the measurement question matters. They show why different stories were proposed. And they show why words like outcome, record, and information are central. Now we take a small reset, just to keep your body relaxed. If you can, take a slow inhale, and then let your exhale be longer than the inhale. As you exhale, repeat the phrase softly in your mind. Possibilities become experiences. Good. With these gentle paradoxes in mind, we can widen the view. Next, we will pause for a moment and then zoom outward, from quantum branches to cosmic ones, at the same steady pace. If this is helping, you can quietly tap save, so it is here tonight or tomorrow. And if you want, type the last fact number you remember before sleep. Or do nothing at all and just keep listening. Now we drift from quantum ideas to the largest stage, the early universe and cosmic inflation. Inflation is a proposed early burst of expansion, brief, fast, and smoothing in its effects. It is meant to stretch space so evenly that large regions look similar in every direction. That calm sameness is something we actually observe when we look at the sky on huge scales. Inflation also helps explain why space appears close to flat, rather than strongly curved. Think of it as a gentle iron, smoothing wrinkles in a hot fabric of space. In this picture, tiny quantum fluctuations are stretched into faint seeds for later structure. Those seeds can grow into galaxies and clusters, slowly, over billions of years. Inflation is a leading idea in cosmology, but its detailed mechanism is still researched. Different models use different fields and shapes of energy, and scientists compare them carefully. So we will hold inflation as a useful hypothesis, not a finished story carved in stone. Now comes a twist that leads to a multiverse, in some versions, eternal inflation. Eternal inflation means inflation might end in some places, but keep going in others. Where it ends, a region can cool down and form a universe like ours, with its own history. Where it continues, space keeps expanding and can keep making more regions later. From far away, this can look like bubbles forming in a vast inflating background. Each bubble is not a soap bubble in air, but a region where the rules changed phase. Inside a bubble, expansion continues in the familiar slower way we call the Big Bang model. Outside, inflation may still be stretching the background faster than signals can travel. That makes bubbles causally separated, meaning they cannot exchange messages in any practical time. Even light has limits, and expanding space can keep regions forever out of contact. So a bubble universe is, in a calm sense, a distant neighborhood behind a one-way horizon. If you like a gentle image, picture islands forming in a foggy ocean that keeps widening. Each island has its own weather, while the ocean between them grows too wide to cross. In physics language, the weather could be the conditions that emerge after inflation ends. These conditions depend on how symmetries break as the universe cools. A symmetry is like a balanced rule, and breaking it is like choosing one stable pattern. Different bubbles could settle into different patterns, with particles or forces behaving slightly differently. Some bubbles might have similar physics to ours, and some might not allow complex structures. This is where multiverse discussions sometimes connect to selection ideas, sometimes called anthropic reasoning. We will keep that connection for later, and for now just note it exists. A key question is whether bubble universes are real physical regions or only mathematical possibilities. In the eternal inflation picture, they are real regions of spacetime, but extremely hard to observe. Hard because observation requires signals, and signals require causal contact. Still, scientists have asked a careful question: could bubbles ever leave subtle traces? One proposed trace is a faint pattern from a bubble collision in the early universe. If two bubble regions formed near each other, their boundaries might have interacted. Such an interaction could, in principle, imprint a gentle asymmetry in the cosmic microwave background. The cosmic microwave background, sometimes shortened to CMB, is the afterglow light from the early universe. It is a quiet map of tiny temperature differences across the sky. Researchers have searched for unusual patterns in that map that might match collision predictions. So far, no clear, widely accepted signature has been confirmed as a bubble collision. That is an important calming boundary. This is an active area, not a settled detection. Even without a confirmed signal, the search helps refine models and sharpen what would count as evidence. In science, looking carefully and finding nothing definite can still teach you something. It can rule out some versions, and it can guide better questions. Another way bubbles could differ is through the value of vacuum energy after inflation. Vacuum energy is like a background pressure of space itself, affecting how fast expansion proceeds. If that value varies across bubbles, the long-term fate of each region could differ. Some might expand gently forever, some might recollapse, and some might become nearly empty. These are quiet, slow differences on timescales far beyond a human life. Now, let's pause for a soft engagement moment, which feels calmer to you tonight. Many bubbles, each separate and quiet, or one single universe with one shared history. You do not need to answer aloud, just notice which picture relaxes your mind. If the bubble picture feels too busy, you can simplify it. Imagine only one bubble, our observable region, floating alone in a dark sea you never need to visit. Inflation, in that sense, becomes a story about why our region looks smooth and uniform on large scales. And eternal inflation becomes a speculative extension that might be true or might not be. Cosmologists weigh these ideas using data, consistency, and how naturally models produce the features we observe. They compare predictions for the spectrum of fluctuations and the kinds of gravitational waves that might be produced. We will not chase details tonight. We just keep the calm shape of the argument. Inflation is motivated by real observations, while the multiverse extension is more uncertain. That uncertainty is not a flaw. It is simply the honest boundary of current evidence. So when you hear multiverse in cosmology, remember it is often a prediction of certain models, not a standalone claim. It is a way of talking about what the mathematics suggests could happen beyond our horizon. And horizons, by design, hide information from us. This brings us to a simpler route to parallel worlds, one that needs no bubbles at all. If space itself is endless, then far away there may be regions that repeat patterns quietly by sheer size. In the next section, we will imagine that endless ocean of space, calm and unhurried. For now, let the bubble universes remain as a soft possibility, like distant lights beyond the fog. Now, let's consider a simpler route to parallel worlds, one that does not require bubbles at all. It begins with a humble fact about astronomy. We can only see a finite region of the universe. Light travels at a finite speed, and the universe has a finite age. So there is a horizon beyond which light has not had time to reach us. The region we can see is called the observable universe. Everything beyond it might exist, but it is outside our view for now. Cosmologists ask a gentle question. Is space beyond our horizon just more of the same, stretching on and on? Or does it end, like the surface of a sphere ends only by looping back? Or is it truly infinite, with no edge at all? Current observations can tell us the universe is very large and close to spatially flat on huge scales. But very large is not the same as infinite. Infinity is a mathematical ideal, and nature may or may not use it. So we will hold the idea softly. Space could be extremely large, perhaps unimaginably larger than what we can observe. And in some models, it could be infinite. If space is infinite, then a curious reasoning exercise appears. In an infinite expanse, patterns can repeat by sheer combinatorics. Combinatorics is the quiet math of counting arrangements. If you have a limited set of possible arrangements in a region, and you have endlessly many regions, repeats become plausible. This is not magic. It is the same calm idea behind repeating patterns in a very long string of random numbers. Given enough length, certain sequences appear again. Now, we must be careful. In the real universe, the number of possible arrangements in a region might be enormous, and whether it is truly finite depends on deeper physics. But the basic intuition is still useful for bedtime. Vastness can make repetition likely in principle. To make this idea more concrete, cosmologists sometimes talk about a Hubble volume. A Hubble volume is a region of space roughly comparable to the patch we can observe, a big local domain defined by cosmic expansion and light travel limits. You can treat it as a universe-sized neighborhood for intuition. The thought is then this: if the universe contains infinitely many Hubble volumes, then there are infinitely many chances for a region like ours to occur again. Not nearby, not reachable, but somewhere in the far distance. This is where people get the image of distant copies. A copy could mean a region with the same large-scale arrangement of galaxies, or in more extreme versions of the argument, a region with the same arrangement of matter down to very fine detail. It is important to keep this calm and modest. This is a reasoning exercise, not a promise. We do not have a telescope that can check beyond the horizon. And even if duplicates exist, space between us might be expanding in a way that keeps them forever out of contact. So the idea does not imply you will meet another you. It does not imply travel routes or hidden doorways. It is simply a way to notice what infinity or near infinity can imply. If you want a soothing metaphor, imagine a night sky as an endless ocean. Our observable region is one calm bay. Beyond the mist is more ocean, perhaps endless. In an endless ocean, wave patterns can resemble each other far away, even if they never touch. Now, a small micro-engagement just to keep your attention gentle. Do you prefer the idea of repetition far away, or branching right here in the quantum sense? You do not need to choose permanently. Just notice what feels quieter tonight. Now, let's underline one subtle point. Even in a vast universe, repetition depends on what counts as the same. If you only care about broad features, repeats might occur relatively often on cosmic scales. If you care about every atom, repeats would be unbelievably far apart if they occur at all. And if the number of possible states in a region is not finite, the simple argument changes. So physicists talk about this carefully, often as a thought tool rather than a claim. It helps clarify what we mean by probability in cosmology. It helps clarify how to reason when you have huge numbers of regions you cannot observe directly. Now we come to a quiet edge case that sometimes appears in these discussions. You may hear the phrase Boltzmann brain. We will keep it brief and gentle. A Boltzmann brain is a hypothetical self-aware observer that forms as a rare fluctuation in a vast universe. It is not presented as something we expect to meet. It is used as a stress test for cosmological models. If a model predicts that most observers are isolated random fluctuations rather than beings with long, stable histories, many scientists see that as a warning sign. So this is not a bedtime horror story. It is a consistency check, like testing a bridge design under unusual loads. The point is to keep models sensible, not to unsettle you. If that phrase feels unpleasant, let it drift away right now. We will not dwell on it. The calm takeaway is this. When you propose an infinite or extremely long-lasting universe, you must also ask what kinds of observers become typical in that model. That question helps filter which cosmological ideas feel coherent and healthy. Now, to keep your mind organized, we will soon sort these multiverse ideas into a neat ladder. A tidy set of shelves like a small library of possibilities. That ladder is often called Tegmark's levels. It will help you file away the difference between faraway repetition, inflationary bubbles, and quantum branching. For now, keep one simple picture. Our view is limited by the speed of light. Space might extend far beyond it. And in a truly enormous space, repetition becomes a quiet mathematical possibility. With that in mind, we can move to the shelf system, a calm set of levels, so your mind can rest without juggling too many forms of many worlds at once. Let's organize the multiverse ideas into a calm set of shelves. This is one popular framework, proposed by physicist Max Tegmark. It does not prove a multiverse exists. It simply names different meanings people use for many universes. Think of it like a filing cabinet for your mind. When a word feels slippery, a good label can make it soft again. Tegmark's map is often described as 4 levels. Each level adds a new kind of elsewhere. Some levels are close to mainstream cosmology. Some levels drift into more philosophical territory. So we will keep our footing and label the ground as we go. Here is a gentle reminder. A framework can be useful, even if you do not accept every shelf in it. Now we begin with level 1. Level 1 is the simplest kind of parallel universe. It is just more space beyond our horizon. We see only a finite region because light has limits and time has limits. But space may continue far beyond what we can observe. In level 1, the laws of physics are the same everywhere. What differs are the initial conditions, the particular arrangements of matter and energy. So level 1 parallels are like distant regions with different cosmic weather. They are not separated by different laws, only by distance. This level connects directly to the idea of repetition in a vast or infinite universe. If space is extremely large, similar patterns could occur far away, not because the universe is copying itself on purpose, but because there are only so many ways to arrange a region, and there may be many regions. Still, this is a reasoning tool, not a travel plan. Even if level 1 repeats exist, they are likely beyond any practical reach. The calm point is simple. Level 1 is same physics farther away. Now we move to level 2. Level 2 is often tied to inflation, especially eternal inflation scenarios. In some inflation models, different regions stop inflating at different times. Each region that stops can form a bubble universe with its own observable patch. These bubbles can be separated by expanding space that keeps them causally apart. Level 2 adds a deeper kind of difference than level 1. In level 2, different bubbles might not share the same low-energy details of physics. For example, symmetry breaking could settle differently in different bubbles. That can change which particles are stable or how forces behave at low energies. Sometimes people also discuss different values of constants across bubbles in certain models. This is one reason level 2 is often linked to many possible settings for physics. It can feel like a multiverse of different rule flavors, not just different starting layouts. But we keep a gentle caution here. Inflation itself is strongly motivated, yet the multiverse extension is harder to confirm directly. And whether constants truly vary depends on details that are still researched. So level 2 is a plausible branch of theory, but not a settled observation. A calm way to file it is this. Level 2 is different bubbles, possibly different conditions. Now we move to level 3. Level 3 is the many worlds picture from quantum mechanics. Notice the shift. Level 3 does not require extra faraway space. It is not about distant regions beyond a horizon. It is about branching outcomes in the quantum description. In this level, the wave function evolves smoothly and measurement is just interaction. Different outcomes become separate branches when they stop interfering in practice. Decoherence is the quiet mechanism that helps explain that separation of branches. So level 3 is many histories, not many faraway places. In a sense, it is parallel universes stacked in the space of possibilities, not across galaxies. This is why people sometimes mix up levels when they hear the word multiverse. Level 1 and 2 are cosmological. Level 3 is quantum. They can be discussed together, but they live in different parts of physics. Now we reach level 4, the boldest shelf. Level 4 suggests that reality might include not just different initial conditions or different constants or different branches. It suggests that different mathematical structures themselves could correspond to different realities. In this view, if a set of mathematical rules is self-consistent, it exists in the same broad sense that our universe exists. This is a philosophical proposal as much as a physical one. Some people find it elegant. Some people find it too unconstrained to be scientific. And many physicists treat it as an interesting idea, but not an empirically grounded claim. So we label level 4 carefully. It is not established by experiment. It is a speculative extension about what existence might mean. If you want a calm summary, you can keep this ordering in one breath. Level 1 is farther space with the same laws. Level 2 is inflationary bubbles that might differ in conditions. Level 3 is quantum branching without needing extra space. Level 4 is the idea that mathematics itself might come in many realities. Now, a small engagement moment to help your mind settle. If you had to pick one level to fall asleep to, which would you choose? Level 1, Level 2, Level 3, or Level 4? You do not need to answer out loud. Just notice which shelf feels the quietest. Some people prefer Level 1 because it is just distance and geography. Some people prefer level 3 because it is one equation told consistently. And some people prefer level 2 because it turns the early universe into a gentle garden of bubbles. If level 4 feels too abstract, it is completely fine to set it down. This framework is here to reduce mental clutter, not to add it. One more calming point before we move on. These levels can overlap in conversations, but they are not automatically linked in nature. A universe could be vast without many worlds being true. Or many worlds could be true without cosmic bubbles being real. And inflation could be true without leading to a multiverse extension. So the levels are categories, not a chain of proof. Now that our shelves are labeled, we can take the next step. We will move into a theory that naturally suggests many possible settings for physics. That takes us to strings and extra dimensions, slowly and gently. If you would like, leave a tiny comment with just one number, 1, 2, 3, or 4. It helps me know which level feels most calming for you. Or simply keep listening, no rush at all. Now we step into a different kind of multiverse conversation, one built from mathematics. This is the world of string theory and extra dimensions. We will keep a clear boundary from the start. String theory is a powerful framework, but it is not confirmed by direct experiment. So tonight, treat it as a carefully explored map. not as a finished photograph of reality. In ordinary life, we experience 3 dimensions of space and 1 of time. Up and down, left and right, forward and back, and then the flow of moments. Some theoretical approaches suggest there may be additional spatial dimensions, not big, open dimensions you could walk into, but compact, hidden directions that are curled up very small. A simple image is a garden hose seen from far away. From a distance, it looks like a one-dimensional line. Up close, you notice a circular direction wrapped around it. In the same way, a point in our space could, in theory, have tiny extra directions attached. If those directions are extremely small, you would not notice them directly. But they could still affect physics indirectly. They could shape which kinds of particles exist and how they interact. They could influence masses, charges, and symmetry patterns. So extra dimensions are not introduced as fantasy hallways. They are introduced because the mathematics of certain theories becomes consistent and elegant with them. Now, a soft engagement moment just to keep your attention comfortable. Does the idea of hidden dimensions feel cozy like secret hallways, or does it feel too abstract? You do not need to answer. Just notice what your mind does and let it settle. In string theory, the basic idea is that the fundamental building blocks are not point particles. They are tiny vibrating strings. Different vibration modes show up as different particles. This is one reason the theory is sometimes praised for unifying forces and matter in one structure. But that unification comes with many mathematical possibilities. To connect string theory to our observed world, the extra dimensions must be shaped in particular ways. This process is often called compactification. Compactification means choosing a geometry for the extra dimensions, like choosing the shape of a folded space. Different shapes can lead to different effective physics at low energies. Low energies here means the energies we can access in laboratories and in the current universe. So you can imagine string theory offering not one single predicted universe, but a menu of possible universes. This menu is sometimes called the string landscape. Landscape is a good word because it suggests many valleys and many stable resting places. Each valley corresponds to a different solution, a different vacuum state, a different set of effective laws. In one valley, certain particles might be light. In another, they might be heavy or absent. In one valley, the strengths of forces might take one set of values. In another, they might take slightly different values. These are not changes you can dial with a knob in your room. They are different consistent solutions of the underlying equations. This is one reason multiverse talk appears in string discussions. If the theory allows many stable solutions, one question is why we find ourselves in this particular one. Some researchers connect this to cosmology. They imagine the early universe exploring parts of the landscape as it evolves. In certain scenarios, different regions might settle into different valleys, like different bubble universes with different effective physics. That links back to the level 2 idea we discussed earlier, but we do not have to tie them tightly. It is enough to say this. The string landscape offers many possible low-energy worlds. Now we come to a topic that can feel sharp if handled carelessly, so we will handle it gently. Vacuum energy and fine-tuning. Vacuum energy is the energy associated with empty space. In cosmology, it can act like a pressure that affects expansion. A small positive vacuum energy can cause the universe to accelerate outward over time. If vacuum energy were much larger in magnitude, the universe's history could look very different. It might expand too quickly for galaxies to form, or it might recollapse rapidly depending on the sign and size. So the observed small value of vacuum energy has inspired many discussions. Some people see it as a clue that we are missing a piece of theory. Some people explore whether a landscape of possible vacuum energies could help explain why we observe a small one. This is where anthropic reasoning sometimes enters the conversation. Anthropic reasoning in its calm form is simply selection logic. It says that any observer will only find themselves in a region compatible with observers. So, if many regions exist with different vacuum energies, Observers would naturally be found in the rare regions where complex structure can arise. This is not a proof. It is not a victory lap. It is a style of explanation that some find useful and others find unsatisfying. And it remains an active research conversation, not a settled conclusion. For bedtime, the safest takeaway is modest. Small changes in vacuum energy can have large effects on cosmic history. Some frameworks, like a landscape of possibilities, offer one way to think about why our value might be small, but the full story is still being worked out. Now we place another clear boundary: what string theory predicts versus what we have measured. String theory is mathematically rich. It has inspired deep results in quantum field theory, gravity, and geometry. It provides candidate descriptions of quantum gravity, a long-sought goal. But direct experimental confirmation is challenging. One reason is scale. The characteristic size of the strings and extra dimensions might be far smaller than we can probe directly. Another reason is flexibility. With many possible compactifications, it can be hard to derive a single unique low-energy prediction that must be true. Researchers therefore look for indirect hints. They look for consistency conditions, mathematical structures that match known physics, and possible cosmological implications. They also study how symmetries might emerge and how certain particle patterns could arise. Sometimes people hope for signatures at high-energy colliders or subtle cosmological imprints. But we should not promise what has not been found. So our calm summary is this: string theory is a framework with extra dimensions that can be compact and hidden. Different ways of shaping those dimensions can yield different effective physics. That variety creates a landscape, a menu of possible low-energy worlds. This is one route by which multiverse ideas appear in the context of strings. And questions about vacuum energy and selection are part of the ongoing conversation. If you feel your attention drifting, you can keep one simple image: a tiny folded space curled up inside each point of ordinary space. Different folds, different patterns of physics. Now we set up the next step, which is related and very visual. Some string-inspired cosmologies picture our universe as a kind of surface, a brain, floating in a larger space. That larger space is sometimes called the bulk. We will not make it loud. We will treat it like a soothing image, a soft geometric ocean. So from curled dimensions, we will move to brains and cycles next. A gentle shift from hidden directions to wider cosmic pictures. Now we stay in the same neighborhood of ideas, but shift the picture. Instead of tiny curled dimensions inside each point, imagine a larger space that can hold surfaces. In some models, our entire observable universe could be a kind of surface called a brain. Brain is short for membrane. A membrane is a surface that can have thickness in the big space, but still feel like a world to the things living on it. This is an intuition tool, not a confirmed observation, but it is a useful way to picture extra dimensions without heavy mathematics. In a brain world picture, many familiar particles and forces might be confined to the brain. They move along the surface, not freely into the larger space around it. Gravity, however, might be different. Some models allow gravity to leak, at least partly, into the extra dimensions. That can change how gravity behaves at very short distances or at very high energies. Researchers have looked for such changes with careful experiments and collider data. So far, there is no clear, accepted detection of extra dimensions through these routes. But the idea remains a lively part of theoretical exploration. Now, where does many worlds come in here? If one brain can exist, some models allow more than one. You can imagine parallel brains like neighboring sheets in a dark, quiet ocean. Each brain could host its own physics, its own matter, its own history. These would be parallel realities in a literal geometric sense, separated by an extra dimension. In that picture, another universe could be next door, but still unreachable because ordinary particles cannot leave the brain. Gravity might be the one messenger that fills the nearby sheets, but even that is model dependent. So we keep our language gentle. This is a way some theories visualize multiple universes without invoking quantum branching. It is a geometric route to parallelism. Now we slide into a related set of cosmological ideas, often called cyclic or ekpyrotic scenarios. These are not mainstream conclusions, but they are thoughtful proposals. The motivation is partly aesthetic. Some people dislike a universe that begins from a single sharp starting point. They wonder if a smoother story is possible, with phases rather than an absolute beginning. In some cyclic pictures, the universe goes through repeating eras: expansion, then a slow turnaround, then contraction, then a bounce or a renewal. In some ekpyrotic versions, the key event is an interaction between brains in a higher dimensional space. A collision or a near collision is proposed as a trigger for a hot, dense phase like a Big Bang. This can sound dramatic, but we can hold it quietly. It is a proposed mechanism for how a new cosmic era might begin. Whether such scenarios match observations as well as inflation does is debated. Researchers compare predictions for the patterns of primordial fluctuations and gravitational waves. Some cyclic models aim to avoid certain inflationary puzzles while facing their own challenges. So we label them as exploratory and contested. They are part of the landscape of ideas, not the final map. Here is a soft engagement moment, just for your attention. Do you prefer a universe with a single beginning or gentle cycles? You do not need to decide. Just notice which picture feels calmer. If cycles feel soothing, you can think of them like seasons. Not identical repeats, but recurring phases with a similar rhythm. If a single beginning feels simpler, you can hold that too. Either way, cosmology stays honest about what is known and what is proposed. Now we take one more step into a quieter corner, sometimes called quantum cosmology. Quantum cosmology is the attempt to apply quantum ideas to the universe as a whole. That is a delicate task, because the universe has no obvious external observer. So researchers explore different ways to describe beginnings or boundaries in a quantum language. One approach you may hear about is a no-boundary proposal. The phrase suggests a universe that does not start with a sharp edge in time, but emerges smoothly from a quantum description. Think of a rounded hill rather than a cliff. This is not a proven fact. It is a model-building attempt to make the earliest moments mathematically well-behaved. Other approaches discuss the universe in terms of an ensemble of histories. An ensemble is a collection of possible histories that contribute to the overall description. In those frameworks, many histories is not a fantasy. It is part of the calculational method. The question becomes how those histories connect to the single classical story we experience. So even in cosmology, the theme returns. Possibilities become experiences. But we will not linger in abstraction. The purpose of this section is to show that multiverse-like ideas can arise from several routes. Inflationary bubbles are one route. Infinite space is another. Brains are another. Quantum cosmology can add its own ensemble language, and cyclic proposals offer a different rhythm for cosmic history. Each route has different levels of evidence and different open problems. That is why the tone must stay careful. Now we prepare for the practical question that follows. If these ideas are more than stories, can any of them leave traces? Can any of them, even in principle, be tested? In the next section, we turn from imagination to evidence. We will ask what could show up in observations and what the limits might be, and we will do it with calm, careful language so the uncertainty feels safe. It is natural to ask a practical question now. If there are other universes, can we ever test that idea? Tonight, the calm answer is, we can test pieces, but not the whole story. Science moves by checking what leaves traces and admitting what stays out of reach. So we will use careful language, like soft footsteps on a dark floor. First, Let's talk about cosmic tests people discuss with caution. In inflationary bubble pictures, a nearby bubble could, in principle, have collided with ours. A collision might leave a faint imprint in the cosmic microwave background. The cosmic microwave background is sometimes called CMB, like an early light afterglow map. Researchers have searched CMB data for gentle circular features or unusual gradients. These searches are careful because the sky also contains random fluctuations and noise. A pattern that looks special can still be a coincidence in a large data set, so the rule is strict. Extraordinary claims require strong statistical support and repeated scrutiny. Sometimes people mention large-scale anomalies in the CMB. These are features that seem a little unusual on the largest angular scales. They are interesting, but not definitive evidence for a multiverse. Cosmology is difficult because we only have one universe to observe directly. We cannot rerun the universe and see what changes. So we rely on statistics across many regions of the sky and on consistency between datasets. When signals are faint, small choices in analysis can matter. That is why the tone stays modest. A multiverse is a big claim, and big claims need firm footing. Now, a gentle thought that helps with patience. Even if bubble collisions are real, their traces could be extremely subtle. They might be masked by ordinary cosmic variance, the natural randomness of one sky, or they might not have happened close enough to matter for our observable patch. So absence of a clear signature is not a final verdict. But it does mean we should not oversell the idea. The next possible window is gravitational waves. Gravitational waves are ripples of space-time itself, traveling like gentle tremors through the cosmos. We have observed gravitational waves from merging compact objects in the modern universe. A different target is primordial gravitational waves from the very early universe. Primordial means from the earliest times before galaxies existed. A background of primordial gravitational waves would be like a faint cosmic hiss of space-time motion. If detected, it could tell us about physics at energies far beyond any laboratory. This is one path to testing inflation. Inflation is connected to multiverse talk because some multiverse scenarios rely on certain inflation models. Different inflationary models predict different spectra, meaning different patterns across frequencies. Some predict a stronger signal, some predict a weaker one. Some predict distinctive shapes in how the signal changes with scale. So gravitational wave searches can help narrow which early universe stories remain plausible. That is a calm kind of progress. You do not need to prove a multiverse to learn from the early universe. You can test inflationary ideas and see which ones survive. Then, if a surviving model also implies bubbles, the multiverse becomes a more serious inference. Even then, it remains an inference, not a direct photograph of other universes. Another cosmic clue people discuss is polarization patterns in the CMB. Polarization is a gentle alignment of light waves, like a subtle texture in the afterglow map. Certain primordial gravitational waves would leave a characteristic swirled pattern. Experiments look for that pattern with extreme care and extremely clean instruments, because foreground dust and other effects can mimic or contaminate the signal. So again, the pace is slow, and the claims must be careful. Now let's move from the sky to the laboratory. There is another edge where parallel world language appears, quantum foundations. Many worlds is difficult to test directly because it often matches standard quantum predictions. But laboratory experiments can still constrain alternatives. In particular, they can test collapse model parameters and the reach of decoherence explanations. The basic strategy is simple. Make quantum interference in larger and larger systems and see how far it can go. Interference is the crisp signature that superposition remains coherent. When interference holds, it suggests ordinary quantum rules still apply at that scale. When interference fails unexpectedly, it could hint at new physics, or it could reveal hidden noise. So experiments become a quiet battle against vibration, heat, stray light, and uncontrolled interactions. Researchers isolate systems, cool them, and reduce environmental recording. Then they look for clean fringes, stable patterns that would not exist in classical physics alone. They do this with atoms, with molecules, and with carefully engineered mechanical devices. As systems get larger, decoherence becomes stronger and harder to suppress. So the challenge grows, but so does the information we gain. If collapse models are correct, they predict a scale where superposition should fail on its own. If no such failure appears within a tested range, those models get squeezed into smaller corners. This does not prove many worlds. It simply removes certain competing stories or forces them to be more subtle. It also deepens our understanding of decoherence, which is useful regardless of interpretation. So, laboratory tests are like boundary markers. They tell us where quantum behavior is clearly present and where classical appearance emerges. They also teach us how measurement devices become records, physically, without any special observer magic. Now, another calm point about what tests can and cannot do. A multiverse is often a package of claims. Some parts are about well-tested physics, like quantum mechanics or general relativity. Some parts are about extrapolations, like what happens beyond our horizon or at extreme energies. Testing usually reaches the well-tested core first. Then we ask whether the extrapolation is the simplest continuation or one of several options. So the honest conclusion is layered. We can test inflationary predictions about fluctuations and gravitational wave backgrounds. We can test whether quantum coherence survives in increasingly complex systems. We can test whether collapse-like deviations show up within experimental sensitivity. But we cannot point a telescope at another bubble and take a picture. And we cannot step outside the universe to compare it with a control universe. So multiverse talk often lives in the space between data and interpretation. It is a discussion about what the best tested theories might imply when extended. That discussion can be scientific if it stays disciplined. Discipline means comparing models, quantifying uncertainty, and avoiding overreach. It also means being honest about what would change our minds. What observation would support a model, and what observation would weaken it? This is why careful language is not boring. It is how science stays calm and reliable. Here is a soft engagement question to keep your attention steady. Do you find comfort in testable details or in big picture possibilities? Either preference is fine. Some nights you want solid ground, and some nights you want open sky. Now, we will close this section with one soothing summary. Multiverse ideas are not all or nothing. We can test the early universe physics that motivates some multiverse scenarios. We can test quantum behavior at larger scales that informs interpretational debates. And we can remain cautious about claims that outrun what evidence can currently touch. With evidence in mind, we can now drift into the quiet philosophy. We will explore identity, probability, and meaning across branches without spiraling. Just gentle questions and gentle answers with room to rest. If you want a sequel, comment one word for the calmest topic for you: quantum, cosmic, or strings. One quiet word is perfect. Or ignore this and keep listening. No rush. Now we step into philosophy, but we will keep it grounded and calm. Philosophy here means the quiet questions that remain after the math is written. Questions about identity, about probability, and about meaning. If you ever feel your mind speeding up, return to one steady anchor. Your lived experience is a single continuous thread. First, identity across branches. In a many worlds picture, a small quantum event can lead to different outcomes. Those outcomes can become different branches once they stop interfering. In that story, there could be nearby variants of you after certain events. Not in a dramatic way, just in the sense that the world's records differ slightly in different branches. So philosophers ask, are those variants the same person? Or are they better described as related successors? A successor is someone who continues from your past, sharing your memories up to a point, then diverging. This is similar to how we already think about identity over time. You are not identical to your childhood self, yet you feel continuous with them. You share memories, habits, and a body that changes slowly. In branching discussions, the continuity is shared up to a branching moment, then multiple continuities exist in parallel. Some thinkers say identity cannot be one to many, so branching creates multiple successors rather than one continuing self. Others say identity talk is flexible, and what matters is psychological continuity and causal connection. Either way, the bedtime takeaway is gentle. In any branch you experience, you still feel like you. You still remember the moments that led there. And your life still unfolds as a single sequence of experiences, one breath after another. No one experiences being spread across branches. You experience one path. So you do not need to hold the entire tree in your mind. You only need the quiet thread you are actually walking. Now, a soft engagement check-in. Does the multiverse feel like freedom to you or like background noise? Just notice your reaction and let it settle. Next, probability. Probability is the part that can feel most slippery in many worlds. Because if all outcomes exist, what does it mean to say one outcome is more likely? One calming way to frame it is as self-location uncertainty. Before you look at a result, you are uncertain about which future experience you will have. Not because the universe is chaotic, but because the branching structure contains multiple future observer moments related to you. So your uncertainty is about where you will find yourself in that structure. It is like waking in a dark hotel hallway and not knowing which door is yours yet. The doors exist, but your experience will be of one of them. Some philosophers and physicists try to connect this idea to the usual probability rule in quantum mechanics. That usual rule links amplitudes to the chances of outcomes. In many worlds discussions, one approach uses decision theory. Decision theory is the study of how a rational agent should choose under uncertainty. The goal is to show that if you know branching will occur, rational betting behavior leads you to weight branches in the same way the standard rule weights outcomes. That is, you act as if the squared size of an amplitude is a probability weight. Supporters argue this recovers the familiar rule without adding a special collapse. Critics argue that the argument depends on assumptions about rationality or about how to count branches. So the debate continues, and it can get technical. For bedtime, we do not need the debate. We only need a soothing concept. In many worlds, probability can be treated as uncertainty about experience, not cosmic dice rolling in the dark. It is uncertainty about which branch you will occupy after an event from your current point of view. And the weights used in practice are linked to the same mathematical structure that predicts experimental statistics. So the theory remains predictive, not merely poetic. Now, we move from identity and probability to ethics and everyday meaning. This part is important, and we will keep it simple and non-dramatic. Even if a theory says many outcomes exist in some sense, your choices still matter. They matter because you experience the consequences of your actions in your branch. They matter because other people around you are affected in the world you share. And they matter because plans and intentions change what happens next within your lived thread. So, multiverse ideas are not a reason to take reckless risks. They are not a reason to ignore consequences. They are not a reason to treat other people as optional. In every interpretation of quantum mechanics, in every cosmological model, kindness and responsibility still belong to the world you inhabit. If you feel any anxious buzz around nothing matters, you can let it go. The multiverse does not erase meaning. It only changes the way some people picture possibilities. A calm way to say it is this: your choices shape the future you meet, and they shape the lives intertwined with yours. So we can enjoy these ideas as intellectual scenery without letting them disturb ordinary values. Now we plant a small retention loop for what comes next. A lot of stress about parallel universes comes from internet myths. Stories about guaranteed outcomes, secret travel, or messages from other worlds. In the next section, we will gently separate science from those myths. We will name what parallel universes do not imply, so your mind can relax. For now, keep the 3 soft takeaways from this philosophy pause. First, your experience is one continuous thread, even if a theory imagines branching in the background. Second, probability can be understood as uncertainty about which experience you will have, not as uncontrolled chaos. Third, everyday meaning remains grounded because consequences still happen where you live. Now we will move on, calmly, to clear the air. Science on one side, myths on the other, and a quiet mind in the middle. Before we enter the long, sleepy list of facts, let's clear a few myths gently. This is not a scolding section. It is a quiet filter so your mind does not spiral at night. First myth, portals and instant travel. In most serious multiverse models, there is no practical door you can open. Many worlds branching is not like hallways between realities. Branches are usually treated as non-interfering histories once decoherence spreads the records. That means they do not chat, and they do not swap people. Cosmological bubble universes, if they exist, are often causally separated. Causally separated means light and signals cannot reach them in any useful time. So even if other regions exist, the universe's geometry can make them unreachable. Science fiction often imagines travel between worlds because it makes a good story. And that is completely fine. But it is a different category from what physics currently supports. Physics models are constrained by causality, energy, and what can be observed. So you can enjoy portal stories as art while keeping science calm and modest. Second myth, every strange feeling is proof of timelines. A common example is the Mandela effect. People notice a memory that does not match a present-day fact and wonder if reality changed. The calm scientific view is simpler. Human memory is not a perfect recording. It is a reconstruction. We store pieces, and later we rebuild the story from cues. Sometimes we blend details from similar memories. Sometimes we mishear or misread something once, and the error becomes sticky. And social reinforcement can strengthen a shared mistake. If you hear many people confidently repeat the same wrong detail, your brain can begin to feel it is familiar. Familiarity can be mistaken for accuracy. This is a normal feature of memory, not a glitch in the universe. So the Mandela effect is not evidence of hopping realities. It is evidence that brains are human. This clarification helps many people sleep because it removes the feeling that the world is unstable. Reality is not flickering because a logo looked different than you expected. Your mind is just doing the natural, imperfect work of remembering. If you find yourself looping on a memory at night, you can try a soft reframe. My memory is a story my brain is rebuilding, not a photograph. Then, let it drift. Third myth, the multiverse means nothing matters. This is not a scientific conclusion. It is a mood, and moods can change. In every model we discussed, your experience remains singular and meaningful. You live one continuous thread of moments. Your choices still shape what happens next in your life, and they affect other people in the world you share. Physics describes patterns in nature. It does not erase values, relationships, or responsibility. Even if a theory imagines many outcomes in a mathematical sense, you still care, you still learn, you still help, and you still feel consequences. So if the phrase "nothing matters" shows up in your thoughts, you can treat it like background noise, not as wisdom and not as physics. A calmer sentence is this: meaning lives in the experiences we have and in how we treat each other. Now, one small practical engagement moment in case it helps your listening. Do you want the facts slower or gently steady? If you want slower, you can lower playback speed a little. If you want steady, keep it as it is and let the rhythm carry you. From here on, we will move into calm, numbered facts. They are designed to be easy to follow and easy to let go. If you wake up later, you can rejoin at any number without rewinding. And if you fall asleep, nothing is lost. The facts will keep flowing like a quiet river. So take one slow breath, We have cleared the myths. We have kept the science gentle. And now we enter the sleepy part, the list of facts you can drift to. Now we begin the sleepy facts, Quantum Branching Edition, facts 1 through 35. If you fall asleep halfway, nothing breaks, because you can rejoin later at any number and continue from there. Fact 1. Many worlds keeps the Schrödinger equation as the only rule for time evolution, even during measurement. Instead of adding a special collapse moment, it treats measurement as an ordinary physical interaction that becomes part of the same smooth, lawful process. A calm way to hold that idea is to imagine one steady rule running underneath everything, like a quiet metronome. Measurement is not a special cliff. It is just another step in the same rhythm. Fact 2. Branches are defined by the loss of interference between alternatives, not by a visible split in space. When different outcomes stop overlapping in a practical way, they behave like separate histories, even though the underlying quantum description can still include them together. If the word branch feels too sharp, you can soften it into paths that stop overlapping. It is less like splitting wood and more like two echoes that fade away from each other. Fact 3. Decoherence can happen extremely fast for everyday objects because light, air molecules, and heat constantly interact with them. Those tiny interactions spread delicate phase information into the environment, so ordinary things quickly look classical and definite. Fact 4. In many worlds, the full set of outcomes remains present in the wave function structure while you experience only one outcome as your lived thread. Your memories, records, and surroundings all agree with each other inside that thread, which is why it feels like one consistent world. You never need to picture yourself experiencing all outcomes at once. In this story, awareness stays local to one thread, and the rest is background structure you are allowed to ignore. Fact 5. Entanglement ties outcomes together so branches stay internally consistent, like two answers that match when you compare notes. Even when results feel random, the correlations obey the same quantum rules, so the story inside a branch does not fall apart into contradictions. Fact 6. The worlds people talk about in many worlds are usually approximate, like weather systems or coastlines that depend on how closely you look. A branch is a stable pattern of records and correlations, and the boundaries can be fuzzy when the system is not strongly decohered. It is normal that the boundaries feel fuzzy, because physics often uses approximate categories when nature does not draw crisp lines. The calm goal is usefulness, not perfection. Fact 7. Many worlds changes the interpretive story more than it changes the calculation, at least with today's experiments. So far, the strongest laboratory successes of quantum mechanics do not force one interpretation, which is why the debate stays calm and open. So if you notice curiosity rising, you can let it settle again. These interpretations are like different bedtime stories told over the same stable set of equations. Let your shoulders soften for a moment and let the pace stay gentle. Now we continue with measurement and observers. Fact 8. In physics, an observer can be any process that records information, not necessarily a conscious mind. A detector, a screen, or the surrounding environment can serve as the observer because it stores correlations that distinguish one outcome from another. Fact 9. A measuring device becomes entangled with what it measures, linking the system's possible outcomes to different device states. When the device also interacts with the environment, those device states become robust records, making the result feel fixed and stable. A record can be as small as a scattered photon or a tiny heat change. Once the record spreads, the world has a preference for one consistent account of what happened inside your branch. Fact 10. Decoherence explains why macroscopic superpositions are hard to maintain under ordinary conditions, even when the microscopic rules allow superposition. Large objects have countless internal and external interactions, so coherence is lost quickly unless the system is carefully isolated. Fact 11. In standard quantum theory, probabilities follow the Born rule, where the squared size of an amplitude gives the chance of an outcome. This rule is supported by vast experimental evidence, and it is the bridge between the smooth wave description and the statistics we observe. Fact 12. In many worlds, explaining the Born rule is still an active technical and philosophical project, not a finished chapter. Some approaches treat probability as uncertainty about which future experience you will have, and others try to justify branch weights through rational decision principles. We do not need to solve that debate tonight. It is enough to know that researchers take the question seriously and build careful arguments, while staying anchored to the same experimental successes. Fact 13. Wigner's friend shows that different observers can describe the same laboratory setup differently, depending on what they include as the system. The calm lesson is that measurement and records must be defined precisely, because mixing viewpoints can create apparent paradoxes. Fact 14. Even when the story sounds surprising, the mathematics remains consistent and tightly constrained by experiment. Many puzzles come from trying to force quantum events into a single classical narrative, rather than letting the quantum description set the terms of the story. If any sentence feels too technical, you can simply keep the feeling of steadiness. The numbers will continue, and your mind can float on top of them. Take one slow breath in and let the exhale last longer. Now we move to interference, the quiet heartbeat of quantumness. Fact 15. Interference patterns show that probabilities combine in a distinctly quantum way through amplitudes that can reinforce or cancel. This is why repeating an experiment many times yields stable patterns, even if any single detection event feels unpredictable. Fact 16. Witch path information tends to destroy interference because it marks the alternatives with distinguishable records. Even if no one reads the record, the mere entanglement with a path marker can be enough to wash out the overlap that interference requires. Fact 17. Quantum eraser experiments show that interference can reappear when accessible witch path information is removed or made unusable in the right comparison. The effect is about correlations and sorting of data, not about changing the past or sending signals backward in time. When you hear eraser, think information hidden, not history changed. The patterns come from how results are grouped with their partner records, like matching calm pairs in a ledger. Fact 18. Delayed choice experiments do not rewrite earlier events. They change which questions the final data can answer. The quantum formalism stays consistent, while the classical habit of imagining one definite path from start to finish is what gets gently challenged. This is one reason quantum stories can feel slippery in words. The mathematics stays calm, while our everyday habit of imagining a single invisible movie in the middle can quietly fail. Fact 19. Decoherence is often effectively irreversible because information disperses into an enormous number of environmental details. In principle, perfect control could reverse the process, but in practice, the environment is too large, so the lost interference stays lost. Fact 20. Isolation and cooling are key tools for keeping quantum states coherent long enough to study them. Vacuum chambers, shielding, and low temperatures reduce unwanted interactions, letting fragile superpositions and entanglement survive for longer times. Fact 21. The classical world can be viewed as a stable pattern that emerges when certain records become robust under environmental monitoring. These robust records behave like the familiar facts of daily life, because they are continually reinforced by ongoing interactions. Let the pace stay steady, like footsteps on soft carpet. Next are a few facts about other interpretations, offered without taking sides. Fact 22. Copenhagen-like views often emphasize that the theory's job is to predict outcomes of measurements and that deeper metaphysical claims can be optional. This practical attitude has helped generations of physicists do reliable work without needing one final picture of reality. For many people, that practical stance is the most soothing. It says, trust the predictions, do the experiments, and let the deeper picture remain an optional layer you can set down at bedtime. Fact 23. Bohmian mechanics keeps a single world with definite particle positions that follow continuous trajectories. A guiding wave function influences those trajectories, so the theory can reproduce many standard quantum results while offering a more concrete underlying story. Fact 24. Bohmian theories involve non-local dynamics, meaning the guidance can depend on the full configuration of an entangled system. This non-locality still does not allow controllable faster-than-light communication, but it does show that quantum correlations are deeply global in character. Non-local here means connected rather than communicating instantly. The theory can have deep correlations while still respecting the rule that useful messages require ordinary, slower channels. Fact 25. Objective collapse models add a rare, spontaneous collapse process as a new physical ingredient. The collapses are designed to be negligible for tiny systems but increasingly significant for large systems, so definite outcomes emerge without branching histories. Fact 26. Collapse models aim to explain why we see one outcome without appealing to many coexisting branches or to special observer roles. Because they slightly modify standard quantum dynamics, they can make predictions that, in principle, could be tested and constrained. Fact 27. Experiments that push interference to larger objects, like large molecules and carefully controlled mechanical devices, can limit how strong any collapse effect could be. When coherence survives where a collapse model would suppress it, the model's allowed parameter range shrinks. So even when interpretations sound philosophical, experiments still matter. Pushing quantum behavior to larger scales helps us learn which stories remain viable and which need revision. Fact 28. No interpretation has yet won by a decisive experimental distinction across the full range of proposals, although some ideas are ruled out or strongly constrained. For example, experiments support quantum correlations that cannot be explained by purely local hidden variable stories. One more soft breath, and we turn to quantum information. These last facts are meant to feel practical and gentle, like tools laid neatly on a dark table. Fact 29. A qubit can be in a superposition of 0 and 1 relative to a chosen measurement basis, and this superposition becomes useful through interference. You can picture it like a calm compass needle that can point between directions until a measurement asks for a definite reading. Fact 30. Quantum teleportation is a protocol that transfers an unknown quantum state using shared entanglement plus an ordinary classical message. No matter or information travels faster than light, because the classical message is required before the receiving side can complete the reconstruction. Teleportation is a good example of how quantum ideas can sound mystical and still be ordinary physics. It is a protocol, like a recipe, and the recipe includes a classical message that keeps everything safely causal. Fact 31. Quantum computing speedups come from carefully arranged interference that boosts the probabilities of useful answers and suppresses others. It is less like checking every answer loudly, and more like shaping a wave so that the right shoreline is where it gently lands. If you like a calmer metaphor, think of sculpting a wave in a quiet pond. The computation is the shaping, and the measurement is where the wave finally reveals a pattern in counted outcomes. Fact 32. Many worlds' language is sometimes used as a metaphor for branching computational paths, because superposition resembles many coexisting possibilities in one description. As a metaphor, it can be calming, as long as we remember the device follows one quantum evolution rather than traveling between separate places. Fact 33. Quantum error correction is essential, because coherence is fragile and noise is everywhere, even in excellent labs. The basic trick is to spread information across multiple qubits so small disturbances can be detected and corrected without learning the protected state itself. Fact 34. The more a system leaks distinguishing information into its environment, the more classical it behaves in practice. Less leakage means more coherence, more interference, and a wider space of quantum behavior that can be observed and used. Fact 35. A soothing summary is that quantum theory is precise and experimentally reliable, while our interpretations are different ways of telling the same core story. You can rest on the precision and let the competing narratives fade like distant, quiet waves. Take a tiny breath, then we'll shift from quantum branches to cosmic bubbles and vast space. If you are still awake, type the last fact number you remember, just the number. It makes it easy to restart from that spot next time. Or do nothing and let the audio carry you on. Now we continue with Sleepy Facts, Cosmic Multiverse Edition, Facts 36 through 70. If you like, pick just one fact to hold and let the rest drift by like quiet starlight. Fact 36. Inflation was proposed to explain why the universe looks so smooth and even on very large scales. In many models, a brief early burst of expansion stretches space and gently irons out large wrinkles. Fact 37. Inflation also helps with the horizon problem, the puzzle of why far apart regions look so similar. The idea is that regions now widely separated were once close enough to share conditions before being stretched apart. Fact 38. Many inflation models predict a nearly scale-invariant pattern of primordial fluctuations. That means the early irregularities have a similar character across a wide range of sizes, like a calm, consistent texture. Fact 39. Those early fluctuations can later grow, slowly, into galaxies and the large-scale cosmic web. Gravity amplifies tiny differences over immense time, turning faint unevenness into structure. Fact 40. Not all inflation models imply a multiverse, even if they share the same basic smoothing effect. Some versions end everywhere in a single connected cosmos without producing separate bubble regions. Fact 41. Eternal inflation is a family of ideas where inflation continues in some regions while ending in others. It is a way the equations can allow ongoing expansion in the background, while local pockets settle into quieter evolution. Fact 42. Regions where inflation ends can be described as bubble universes in some frameworks. Each bubble can contain its own observable region, surrounded by space that may keep inflating too quickly to ever cross. If that felt large, let it become simple again. Imagine one quiet bubble, our visible sky, and an ocean of expansion beyond it that you do not need to reach. Fact 43. Bubble regions may be causally disconnected, meaning signals cannot travel between them if space expands the gap faster than light can cross it. This is separation by geometry and timing, not by walls or barriers. Fact 44. Different bubbles could, in principle, realize different symmetry-breaking outcomes as the universe cools. A symmetry-breaking outcome is like choosing one stable pattern out of several possibilities, which can shape low-energy physics. Fact 45. Some discussions allow different effective constants across bubbles depending on the model and how the early fields settle. This is a theoretical possibility in certain scenarios, not a measurement we can currently confirm directly. Fact 46. Bubble collision searches look for subtle patterns that a collision might leave in the cosmic microwave background. Researchers test specific templates and look for faint, statistically meaningful features rather than dramatic marks. Fact 47. So far, no widely accepted collision signature has been confirmed. Interesting candidates have been studied, but the community remains cautious because random fluctuations can imitate patterns. Fact 48. Testing inflation is more feasible than testing all bubbles because inflation can affect measurable features in our own sky. Constraints on fluctuations, polarization, and other signatures can narrow which inflation models remain plausible. Fact 49. Scientific humility is part of the multiverse conversation because the claims are large and the evidence can be indirect. Good work here means careful statistics, clear assumptions, and a willingness to say, not yet. Now we shift to a quieter multiverse idea, sometimes called Level 1. It is simply more space beyond our horizon with the same basic laws. Fact 50. The observable universe is limited by light travel time and cosmic expansion. We see only what light has had time to bring to us, so the horizon is a limit on observation, not necessarily a limit on existence. Fact 51. Beyond the horizon, space could continue with similar physics and similar kinds of matter. The simplest extension is that the universe keeps going, even if we cannot see how far. Fact 52. If space is huge enough, rare patterns become likely somewhere, simply because there are many places for them to occur. Vastness can turn unlikely arrangements into eventual occurrences without any guiding hand. Fact 53. This includes, in theory, regions with histories resembling ours, if the number of possible configurations in a large patch is finite in the relevant sense. The key word is theory, because the distances involved would be unimaginably large. Fact 54. This is a statistical argument, not a practical travel plan. Even if distant copies exist, expansion and causal limits can keep them permanently out of reach, like far shores beyond an endless fog. Fact 55. Cosmology uses probabilities carefully because we only observe one universe, not a repeated sample of universes. That makes inference subtle, and it forces scientists to be explicit about what is assumed and what is actually measured. Fact 56. Typicality assumptions can strongly affect conclusions because they decide what counts as a normal observer or a normal location. When typicality is unclear, scientists treat results as conditional, not as final truths. If you want a small comfort here, it is this. Even if the universe is enormous, your night is local, and your breath is closer than any horizon. Now we return to Tegmark's levels as a filing cabinet, using them as labels rather than as commitments. The point is to keep ideas from blending into one confusing blur. Fact 57. Level 1 refers to beyond horizon regions with the same laws of physics. It is a geography multiverse, where difference comes from distance and initial conditions, not from different rulebooks. Fact 58. Level 2 refers to inflationary bubbles that could have different effective conditions, depending on how the early universe settles. It is a stronger kind of parallelism than Level 1, but also harder to test directly. Fact 59. Level 3 refers to many worlds branching from quantum events, which does not require extra distant space. It is a multiverse of histories rather than a multiverse of faraway locations. Fact 60. Level 3 does not necessarily add more kinds of universes than quantum theory already implies in its mathematics. It mainly changes the interpretation of what the universal wave description is saying about outcomes. Fact 61. Level 4 is the philosophical proposal that all mathematical structures exist as realities. This idea is bold, and it stretches beyond standard empirical practice, so people treat it very differently. Fact 62. Scientists and philosophers disagree widely on Level 4, including whether it belongs to physics or to metaphysics. The disagreement itself is a reminder to keep the label separate from the evidence. Fact 63. The levels help compare ideas without mixing them up, especially when the word multiverse is used loosely. When you know which level someone means, the conversation becomes calmer and clearer. Now we end with a few quiet consistency checks that cosmologists use so the topic stays grounded. These are not scary puzzles, just tools for keeping models sensible. Fact 64. Models are judged by how well they fit data and how many assumptions they add. A model that explains more with fewer extra ingredients is often preferred, as long as it remains consistent with observation. Fact 65. Cosmic microwave background measurements strongly constrain early universe parameters. Tiny temperature and polarization patterns act like a fossil record, limiting which histories could have produced the sky we see. Fact 66. Large-scale structure surveys test cosmological models in complementary ways by mapping how galaxies cluster across space. When different datasets agree, confidence grows, and when they disagree, theories are refined. Fact 67. Some rare observer puzzles are used as stress tests for models to see whether the implied typical observer makes sense. If a model predicts that ordinary observers should be extremely unlikely, scientists treat that as a sign to look closer. Fact 68. If a model predicts that observers are usually very strange, that is a warning sign rather than a bedtime story. The goal is to avoid theories that make our orderly experience wildly atypical without strong supporting evidence. Fact 69. This is part of why Boltzmann brain discussions appear in research, as a check on long-lived or infinite scenarios. The point is not to frighten, but to ensure the model does not make random, short-lived observers dominate the statistics. Fact 70. The calm takeaway is that cosmology uses multiverse ideas cautiously, often as implications of other hypotheses like inflation or vast space. Scientists test what they can label what is speculative and keep the rest as a quiet possibility. Take a soft breath. Next, we will drift into strings, hidden dimensions, and the landscape still numbered, still calm. If you want more of this style, comment one word: quantum, cosmic, or strings. Then let your hands rest and get comfortable. Or skip it and keep listening, no rush. Now we continue with sleepy facts, strings, dimensions, and meaning. from Fact 71 onward. If you get drowsy, let the numbers become a soft rhythm, and keep only whatever feels easiest to hold. Fact 71. In some theories, extra dimensions can be compactified, meaning curled up so small that we do not notice them in daily life. You can picture them as tiny loops attached to each point in space, quiet and hidden. Fact 72. The shape of compact dimensions can influence particle properties we measure, like masses and interaction strengths. In these models, geometry is not just scenery, it gently helps decide what kinds of particles can exist. Fact 73. Different compactifications can lead to different low-energy physics, even if the underlying framework is the same. Low energy here means the physics we see in laboratories and in the current universe, far below the deepest fundamental scale. Fact 74. This variety is one motivation for talking about many possible vacua in string theory, meaning many stable or metastable solutions. A vacuum here is not empty nothingness, it is a particular background state with its own effective rules. Fact 75. The word landscape means many consistent solutions, not many confirmed universes. It is a mathematical menu of possibilities, and nature may choose only one or explore more than one depending on the cosmological story. Fact 76. Direct experimental tests of string-scale physics are currently very difficult because the characteristic energies could be far beyond what we can reach. So much of string theory today is judged by mathematical consistency, indirect links, and whether it can reproduce known physics in the right limits. Fact 77. Even without direct confirmation, string theory has contributed tools used across quantum gravity and mathematical physics. Ideas from strings have influenced how researchers think about black holes, gauge theories, and the deep relationship between geometry and quantum fields. Fact 78. Some discussions link the landscape to why certain constants look special, like the values that allow long-lived stars and stable chemistry. The thought is not that the universe is designed, but that many consistent settings might exist in theory, and some settings naturally support complexity. Fact 79. The anthropic principle appears when selection affects matter, meaning observers can only arise in some conditions. In its calm form, it is simply a reminder that our observations are filtered by the fact that we are here to observe. Fact 80. Anthropic reasoning is controversial, because some see it as useful and others see it as unsatisfying. The disagreement is partly about what counts as explanation in physics, and partly about how testable a landscape picture can become. Fact 81. Vacuum energy, often connected to dark energy, strongly affects cosmic expansion in modern cosmology. A small positive vacuum energy leads to gentle accelerated expansion over time, while other values could reshape cosmic history dramatically. Fact 82. In many models, a very large vacuum energy could prevent galaxies from forming, because space would expand too quickly for matter to clump. This is one reason dark energy appears so often in multiverse debates as a sensitive knob in the story of structure formation. Fact 83. Because vacuum energy is so influential, it becomes a frequent topic in multiverse discussions that involve a landscape of possible values. Some researchers ask whether our small observed value might be typical among observer-friendly regions, while others seek a more direct dynamical explanation. Fact 84. The calm stance is that this remains an active area, not a closed case with one agreed answer. You can let it rest as an open question that motivates careful work, rather than a conclusion you must carry to bed. Fact 85. In some models, our universe could be a brain, a surface embedded in a higher dimensional space. In this picture, many particles are confined to the brain, while the larger space provides the stage on which the brain floats. Fact 86. Other brains, if they exist, would be parallel realities in a geometric sense, like neighboring sheets separated by an extra dimension. They might be close in a higher dimensional space, yet unreachable to ordinary matter that stays on its own brain. Fact 87. Gravity might propagate differently than other forces in certain brain world pictures, sometimes spreading into extra dimensions while other forces remain confined. This is one reason brain models have inspired experimental searches for tiny deviations from familiar gravitational behavior. Fact 88. Some cyclic or ekpyrot scenarios imagine brain interactions shaping cosmic history, such as gentle collisions or approaches that trigger hot dense phases. These ideas are explored as alternatives or companions to inflation, and their status remains debated. Fact 89. Brain ideas are mathematically rich but not yet empirically confirmed in a direct way. That gap between elegant mathematics and difficult measurement is normal in frontier physics, and it is okay to hold it without urgency. Fact 90. Cosmological data can constrain broad classes of early universe behavior, even when we cannot see the deepest mechanisms directly. Measurements of cosmic microwave background patterns, galaxy clustering, and expansion history act like quiet filters on what could have happened. Fact 91. Possible and proven are different words, and sleep can live in that gentle gap. It is soothing to let a theory be a maybe while still appreciating the care and creativity behind it. Fact 92. Some approaches treat the early universe as a quantum system with many possible histories, rather than one fixed classical path from the start. The goal is to use quantum principles to describe beginnings, where classical intuition may not apply cleanly. Fact 93. Path integral methods weigh histories by their action, like many quiet routes through a landscape that contribute to an overall pattern. You do not need the math tonight, only the image of many possible paths adding up to a stable prediction. Fact 94. No boundary and related proposals are ways to pose initial conditions mathematically, aiming for a smooth description rather than a sharp edge. The language can sound mysterious, but it is often just careful bookkeeping for what the beginning means in equations. Fact 95. Different approaches can agree on predictions while differing in interpretation, which is common across physics. When two stories give the same measurable results, scientists often focus on sharper questions that might one day separate them. Fact 96. In quantum gravity, time can behave differently than in everyday intuition, sometimes emerging from deeper relationships rather than being a fixed background clock. This is one reason discussions of the earliest moments can feel subtle, because the usual notion of time may be part of what is being explained. Fact 97. That is why questions about before the Big Bang are delicate, because before assumes a time order that may not exist in the same way at the deepest level. Some models replace before with other regions of a more complete description, which can be calmer to imagine. Fact 98. Subtle does not mean scary, it simply means carefully defined. When the language feels slippery, you can return to the idea that physics seeks consistency and predictive power, even when the pictures are abstract. Fact 99. In many worlds, after a quantum event, multiple successor experiences may exist in the theory, each continuing from the same past up to a branching point. This is a statement about the structure of the description, not a claim that anyone feels split or scattered. Fact 100. Philosophers debate whether these successors count as separate persons or as continuations of one pattern that diverges. Either way, each successor has a coherent inner life, with memories that flow smoothly from the shared past. Fact 101. Probability can be framed as uncertainty about which successor you will experience from your current perspective. It can feel like not knowing which page you will land on next, even though the book contains many possible continuations in the abstract story. Fact 102. Some arguments use decision theory to connect this to the Born rule, suggesting rational choices should weight outcomes in the usual quantum way. Supporters see this as a bridge from structure to probability, while critics question the assumptions, so the discussion continues. Fact 103. None of this changes everyday responsibility, because actions still affect real people in the world you experience. Even if a theory speaks of many outcomes, your lived consequences remain local, tangible, and meaningful. Fact 104. Multiverse ideas are not a reason to seek danger or ignore consequences, and physics does not recommend reckless behavior. A calm science mindset treats life as precious, because your experience and the experiences of others are the realities you actually share. Fact 105. A gentle grounding is that your next breath is here in this moment. Whatever theories exist in the background, you are safe to return to the simple rhythm of breathing and listening. Fact 106. Interpretations can differ while sharing the same successful predictions, and that is a normal feature of deep theories. When the math works reliably, the debate often shifts to what the math is saying about reality, and that debate can remain calm and productive. Fact 107. Scientists often prefer models that explain more with fewer added assumptions, but they can disagree on what counts as fewer. Sometimes a theory looks simpler in equations, and sometimes it looks simpler in its story, and those can be different kinds of simplicity. Fact 108. Testability can mean direct tests or indirect constraints from well-tested physics that limit what a new idea could do. Many frontier ideas survive by being consistent with everything we already know, even if they are not yet directly confirmed. Fact 109. Cosmology relies on statistics carefully because we observe one universe from one location, not a repeated sample. This is why researchers are cautious about overinterpreting faint anomalies and why uncertainty is treated as part of the result. Fact 110. The multiverse is a set of ideas, not a single theory with one agreed set of equations. Different fields use the word for different reasons, so a calm mind always asks which kind of multiverse is being discussed. Fact 111. Many debates are about what the math means, not whether the math works in experiments. It is possible for a theory to be extraordinarily predictive and still leave room for different metaphysical pictures. Fact 112. Calm repetition helps sleep, so you may hear ideas more than once across replays, and that is intentional. Familiarity turns complex topics into soft background, like a song you do not need to follow note by note. Fact 113. Curiosity can be soothing when it is structured and predictable, and numbers provide that structure. You do not have to chase every implication. You can simply let each fact land and then pass on. Fact 114. If you fall asleep, your brain can still benefit from gentle, non-stressful focus because it shifts attention away from racing thoughts. The content is here as a calm track, not as homework. Fact 115. If you wake, you can rejoin at any point, and there is no need to catch up. The facts are designed to be modular, like stepping stones you can land on without remembering the whole path. Fact 116. The universe is big enough to be mysterious without being threatening, and mystery can be a soft place to rest. You can let the unknown feel like a wide night sky, open and quiet. Fact 117. Your mind can rest inside that mystery without needing to solve it tonight. Not knowing everything is not a failure. It is the normal human condition, and it can be peaceful. Fact 118. Quiet thought. Even one reality contains endless detail, more than a lifetime can fully explore. So the multiverse is not required for wonder. It is only one way to organize wonder into different shelves. Fact 119. Quiet thought. If many realities exist, they would still be made of simple rules, repeated with gentle variation. Complexity can arise from simple rules, the way snowflakes differ while following the same calm physics. Fact 120. Quiet thought. Simple rules can feel like a lullaby because they are steady even when outcomes vary. A predictable framework can be comforting, like waves that always return to shore. Fact 121. When you hear grand claims online, a soothing habit is to ask what would count as evidence and what remains philosophy. That single question often turns anxiety into clarity and clarity into calm. Fact 122. It is okay to enjoy beautiful ideas without demanding certainty, because science grows by questioning its own edges. Appreciation and skepticism can coexist gently, like two hands holding the same cup. Fact 123. In physics, words are often imperfect shadows of equations, so disagreements can start from language rather than from data. When that happens, the calm move is to slow down and define terms, then let the urgency dissolve. Fact 124. Many models are designed to be self-consistent first because inconsistency is an immediate problem, while incompleteness is a normal stage. Consistency is like a quiet floor you can stand on, even while the room is still being built. Fact 125. A useful bedtime distinction is between a metaphor and a mechanism, because metaphors are meant to guide intuition, not to be literal. When a metaphor starts to feel spooky, you can set it down and keep only what is measured. Fact 126. Whatever the cosmos contains, your nervous system still responds best to gentle rhythms, warmth, and steady breathing. This is a reminder that the simplest supports for sleep are always available, even under the biggest ideas. Fact 127. If parallel universes exist, they do not make your current life less real, because reality is experienced locally, moment by moment. The chair under you, the air you breathe, and the sound you hear are enough to be grounded. Fact 128. Many scientists hold multiverse possibilities lightly because strong claims deserve strong support, and support takes time. This patience is not hesitation, it is care, and care is a calming attitude to borrow. Fact 129. A gentle closing thought is that meaning is not a physics parameter, it is something minds and communities build together. Even if the universe is vast, kindness remains small enough to be practiced here. Fact 130. One last grounding line for this section is simple. Your next breath is here, and it is enough. Now we will slow down further with a looping recap designed for repeat listening and effortless drifting. Now we slow down into a looping recap for sleep. This part is designed for replays and for drifting. If you only catch fragments, that is perfect. We will move through a few soft loops, and each loop can stand alone. Loop 1, the 3 multiverse families, slowly. First, the cosmic multiverse family. This includes inflationary bubbles, where different regions stop inflating at different times. It can also include vast space beyond our horizon, where distant regions simply lie too far away to see. Cosmic multiverse ideas are about geography and early universe history. Second, the quantum branching family. This is the many-world style picture, where the Schrödinger equation keeps running without a special collapse rule. Decoherence explains why alternatives stop overlapping in practice, so branches stop interfering. Quantum multiverse ideas are about measurement, records, and histories, not about distant galaxies. Third, the theory landscape family. This includes frameworks where there are many possible low-energy settings for physics, depending on how extra dimensions or fields settle. In string discussions, this is sometimes called a landscape of vacua, a menu of consistent solutions. Landscape ideas are about many possible rule settings, not many confirmed universes. That completes loop 1. Cosmic bubbles and vastness. Quantum branching and decoherence. Theory landscapes and many possible settings. If you want, choose one family to hold and let the others fade. Loop 2. What we can test versus what we infer. Quantum theory, as a set of predictions, is tested extremely well in countless experiments. Interference, entanglement, and the statistics of measurements all match the math with remarkable precision. But interpretations differ on what the math means, and those interpretations can share the same predictions. So we test the core quantum rules strongly, while the stories remain optional layers. In cosmology, we test many parameters through careful measurements of the sky. The cosmic microwave background, galaxy surveys, and expansion data all act as checks on early universe models. Inflation is supported in broad strokes because it explains several features well, but its detailed mechanism is still researched. And multiverse claims are often implications of other hypotheses held with appropriate caution. We can test some fingerprints of early universe physics, but we cannot directly observe other bubbles beyond our horizon. So the calm stance is layered. Strong tests for certain pieces, careful inference for bigger pictures, and patient uncertainty where evidence cannot reach yet. That completes loop 2. We test the math very well. We infer some implications carefully. We leave the rest softly open. Loop 3. A calm meaning statement. Let the rest be background, like distant stars. Many possibilities in theory do not erase meaning in practice. Meaning happens where you live, in the world you experience. Your experience is one gentle thread through tonight. One breath, then the next. One sentence, then silence. Even if the universe is vast, your mind can be small and safe. You do not have to decide anything tonight. You can let wonder exist without turning into worry. That completes loop 3. Background stars. Local meaning. 1. Gentle thread. Loop 4. Soft counting with multiverse imagery. If you lose track, that is the point. You can start again at 1 anytime. We will count 1 to 10 slowly, and we will pair each number with a quiet image. 1. A ripple on dark water. 2. A second ripple overlapping softly. 3. A branching path that fades into mist. 4. A bubble of faint light in deep space. 5. A far horizon curve, calm and distant. 6. A tiny curled dimension, like a hidden loop. 7. A soft sheet, like a brain drifting gently. 8. A quiet lattice of geometry, barely seen. 9. A star field that feels endless but harmless. 10. A slow exhale, returning to simple darkness. If your jaw is tight, let it loosen. If your tongue is pressed to the roof of your mouth, let it rest. Soften consonants in your own inner voice if you notice them. Nothing sharp is needed now. We can count again, if you like. 1. Ripple. 2. Ripple. 3. Branch. 4. Bubble. 5. Horizon. 6. Dimension. 7. Sheet. 8. Lattice. 9. Stars. 10. Exhale. That completes loop 4. Counting can be a raft, and you can float on it without steering. Loop 5. The final open loop payoff and release. At the start, we mentioned an almost testable idea. Not a portal, not a certainty, just a place where evidence might touch a big question. The idea is that early universe physics can leave statistical fingerprints. Researchers look for those fingerprints in the cosmic microwave background patterns. They also look for them in possible gravitational wave backgrounds from the early universe. These are not guaranteed discoveries, and signals can be faint. But they are examples of how big ideas connect back to measurable traces. So the multiverse, when spoken carefully, can stay connected to the scientific method. And now, the release. No need to decide tonight. No need to solve anything. Let the question float, then fade, like a cloud passing in front of stars. Here is a quiet closing phrase to hold, and then let go. Possibility becomes peace. Possibility becomes peace. Possibility becomes peace. If you are still awake, you can choose one loop to replay in your mind. Loop 1, the 3 families. Loop 2, tests and inferences. Loop 3, meaning stays local. Loop 4, counting with images. Or you can choose none and simply listen. From here, we will close in under a minute. You can let the audio keep rolling as you fall asleep. If you would like another 2-hour calm science sleep, subscribe so it is here when you need it. And tell me your next topic in a comment: black holes, deep ocean biology, or the history of numbers. Good night and breathe gently.